Our speaker tonight is Tom, our very own VMC coordinator, and he's going to give us an update about the James Webb Space Telescope.
We should kill some lights. It's space, so it should be dark. So in December of 1995, the director of the Institute decided to point the Hubble Space Telescope at a blank patch of sky. This is all there was in that field. This is all you could see from the ground. There's like less than a half a dozen stars in that image. And after about 130 hours over 10 days, over 340 exposures, we found this, the Hubble Deep Field. The sky is full of galaxies. There are galaxies everywhere if you just look deep enough. Deep means fainter things, further back in time. There's over 3,000 galaxies in that image. And it took 10 days to make it. So in March of this year, while nobody was on vacation and the whole world was watching, a bunch of us got together in a conference room in the Mission Operations Center to look at this. We didn't cheat. We actually waited until we were all in the conference room. There was probably 100 people in there before we looked at this image. This is the fine phasing 3 image for the James Webb Space Telescope. This is as good as it gets. This is an incredibly good image. It's the most powerful astronomical telescope ever built. The image quality is, it's just spectacular. You run out of words to say. We said that the goal was to get to 150 nanometers of wavefront error. What that means is the surface of the mirror at every point is within 150 nanometers of a perfect parabola. And we're better than 80. The official number we're publishing is 80, but in fact we haven't been above 80 for more than a dozen days since March. We're never that high for more than a couple of days. We just do a correction. But the interesting thing about this picture is not the giant, crisp, lovely star. It's the stuff in the background. It's all this stuff back here. Galaxies. The sky is full of galaxies. But this isn't over 10 days. This is over 2,000 seconds. Every Webb field is a deep field. And so if you look at this image a little closer, this isn't all of them. This is just the brightest 205 objects that aren't stars. And there's all kinds of galaxies there. There's big, nice spirals. There's, I don't know what that is. It's a mess. There's this guy here. It's another mess. Here's a galaxy merger in process. Here's another galaxy merger in process. Every kind of galaxy you can imagine in a 2,000 second image. So this is the story of how we got here. This is what I do for a living. This is what I do for fun. I have 3 wings sitting in my dining room, behind my dining room table. And I have one more on the bench that's taken a couple days ago now. And that's where I am. And when I get a little bit further along, Chris wants me to talk about wood airplanes. I think they're kind of fun. I don't know what it is you guys see in metal airplanes. We should have known that we were going to get galaxies like that, but we didn't. This is a movie. Look at it for a second, you might spot it. You see it yet? And also look right here, it gets brighter. The part of the movie without that dot is a model. It's what we did at our last rehearsal, assuming that we had a good deployment, a really good deployment. So this is what we thought we would get if things went really well. And it's a little better in reality. Not a lot better, but a little. And this looks like it might be a hot pixel. The problem is, it's not a pixel. It's got shape to it. It's a background object. We didn't know what it was yet, but we knew something was going on. We knew we had a really good telescope at this point. And this was a few weeks before that fine phasing image. But even even at that point, even when we were just stacked before we got phased. So phasing is the process of getting all the mirrors to exactly the same height so that all the light arrives at the same time. Stacking is just getting all the segments pointing at the same spot. This is an 18 segment mirror. I'll have a picture of it later. All right, but even in this stacked but not phased image, there's galaxies everywhere. Big ones, near ones, bright ones, but galaxies in the background. We had a problem early on with the observatory. Actually, we still have the same problem. It's not actually a thing in the observatory. It's an error in the protocol for talking to the observatory. We talk over CFDP, which is an internet protocol for objects with very high latency. Now, usually that's used for things like talking to geosynchronous satellites, where the delay is like a second round trip. We're a little further out. We're 1 million miles away. So we have a very long internet connection to the observatory. And as a result, the bug in the protocol was that we would fill up the recorder and then we wouldn't get any data back. The last thing that we did wouldn't come down, and we had to poke it. So we started taking these throwaway images. This is a throwaway image. We never intended to even look at it. And there's galaxies in the background. There's galaxy mergers in the background. There's all sorts of stuff going on. This is a 300-second image. This isn't even a science instrument. This is the fine guidance sensor. It uses the same kind of detector, but it's got no filters, it's got no grisms, it's got nothing. It's just wide open, looking at the sky. And Marcio Melendez, who's one of our wavefront analysts, noticed that he could see really good stuff in the FGS image. And again, these are 300-second images. That's about as short as you can get with Webb, is 300 seconds. And he wondered, if you just started stacking these up the same way that we did with Hubble, what would you get? And so he just kept taking the same field in the FGS over and over again. This is 30 hours. This was, for a few weeks, the deepest image of the universe ever seen by humans. And again, it's throwaway stuff. This isn't a science instrument. This is just what we could see just by looking. And look at this thing up here. I mean, look at that. That's a fantastic, gorgeous galaxy. This guy down here. There's a lot going on here. This is a galaxy merger. This is a background galaxy, but this is a galaxy merger. So this is one galaxy, this is another galaxy, and they're colliding.
Can you just slide the projector a little bit to the left side?
Oh, am I off
It's
again?
so
Okay.
beautiful. I want to see all of them.
Yeah, okay.
Thank you.
There we go. And it's gotten a little bit out of its keyhole, too. Yeah, I can't do more than that. So we started looking at, once we got the telescope phase, we started commissioning the instruments. And we ran into more surprises. On the left is Spitzer. Spitzer was a smaller, older infrared telescope. It was, for many years, the highest resolution infrared telescope in space. It was cryogen cooled, and when it ran out of cryogen, they did a warm program, but it really didn't work out. And so Spitzer died a few years ago. On the right is Miri. One of the guys on the Miri team had worked on Spitzer for years. And if you look at all this stuff in the background here, it kind of looks all waffly. He thought that was noise. And for years, he tried to calibrate out all that noise. And it was, he thought for a long time it had to be things like amplifier noise or cross-pixel capacitance or something. He didn't know what it was, couldn't figure it out. Well, it turns out they were galaxies in the background. For years, when we did our exercises, for the last 2 years, we did nothing but practice commissioning the observatory. And we would do these maps of the sky based on star surveys. We never once put a galaxy in.
I'm going to ask a stupid question, but what defines a galaxy?
So a galaxy is a large collection of stars. So we live inside a galaxy.
Right.
They're typically hundreds of light years across. And there's billions of stars in each galaxy. All right, so we live inside the Milky Way galaxy. Our nearest neighbor is the Large Magellanic Cloud, which is a dwarf galaxy. The really pretty pictures you see of big spirals, that's the Andromeda galaxy, which is coming straight at us at 60,000 kilometers a second. It's not going to arrive anytime soon. So with MIRI, we finally solved the problem of the background noise in Spitzer. It's not noise at all. I was actually hoping, because we had high clouds tonight, that I would get to see this, but these are what's called noctilucent clouds. Noctilucent is just Latin for bright at night. These are clouds that are lit from below. So the sun's already gone down over the horizon, and it's shining up on these clouds. So hang on to that thought for a second. This is an extended bright this is Jupiter. This is an engineering image. The purpose of this was to put a large, bright object in the field of view and see if we got something else, some sort of stray light feature, to see if we could still guide. There was concern that light would spread out from Jupiter and screw up the guider, and we wouldn't be able to lock onto things. And so everything would be smeared when you were doing moving targets. Jupiter's a fairly slow moving target. We talk about it in milliarc seconds per second. So Jupiter is 3.6 milliarc seconds per second. So that's a very slow move. We didn't have any trouble tracking Jupiter. Oh boy, did we not have trouble. And we didn't see a whole lot of difficult straight light features, but this feature right here, the Great Red Spot, Cassini called that the permanent spot. For 350 years, that spot has been there. And what we've learned in the past few years is that spot is breaking up. And within a couple of decades, it'll be gone. Maybe not within my lifetime, but within my daughter's lifetime. So for 400 years, people have assumed that that's a permanent spot, but it's not. It won't be much longer before it's gone.
Are those speckles Jupiter's moons?
No, those speckles are mostly noise.
Okay.
But we did see moons. If you overexpose a little bit, so anything that's a point source has diffraction spikes. So stars typically have diffraction spikes. Anything that's not a point source won't have diffraction spikes for annoying math reasons. If you overexpose Jupiter, you see a couple of additional things. I'm going to come out for this one because this is cool. All right, so right here is the Jupiter ring system. See it right there? Right? This is a bunch of noise on the detector. We fix that normally by dithering around. When we do science, what we do is we take a picture here, and then we move over and we take the same picture, and then we can fill in all the bad pixels and do cosmic ray rejection, all that crap. This is one of the moons. I've forgotten which one already. But the interesting feature, the most interesting feature, which, let's see, who was it? One of the NIRCam guys just happened to notice it when he was trying to figure out if things were stray light. This is not stray light. This is not an echo. This is a real feature. This is the dark side of Jupiter right here. So the sun's over there, over where Chris is, and it's shining on Jupiter. And you can just see a little bit of an edge of the dark side of Jupiter. And beyond the dark side, lit from below, are these clouds. So now we know something new about Jupiter. We know that Jupiter has a stratified atmosphere like ours, right? Our atmosphere is not this monolithic stack of air where the moisture is evenly distributed all the way up the column, right? One of the things we learn is the clouds are in layers because of changes in temperature where things actually precipitate out. Jupiter has the same sort of feature, only that's methane, not water vapor.
How do you figure that out?
Mostly spectrometry. In this case, we had we already had a lot of images of Jupiter, and John was able to go back and look at things and identify where the cloud appeared on the dark side. So we know it's methane because the specter of Jupiter is methane, basically, at high altitudes. But we hadn't seen this particular feature before. It was hypothesized that it should be there, that it should be stratified. This is the first time anybody's actually directly imaged it.
So that means there's a lot of cows?
Spherical cows in a vacuum.
Real quick.
Just real quick, is the James Webb Space Telescope powerful enough for you guys to actually see, static discharges between the cloud layers, or have you guys not seen them?
Probably not. That's a fun question. I bet we could on Mars, but I don't know about Jupiter. I don't think I have any pictures of Mars. No, I don't. Okay. One of the things, so I'm glad somebody asked about spectroscopy. One of the things we do is multi-object spectroscopy. This is called slitless multi-object spectroscopy. It's a fun thing to do. Again, it's a problem. There's supposed to be a couple hundred stars. There are, in fact, a couple hundred stars in this image. The problem is there's a couple of thousand background galaxies. The software to do the calibration and reduction of multi-object spectroscopy assumed there would be a couple hundred stars. So it would go through, find each source, make a file, do the spectral analysis of each of those files. But when you get a couple of thousand of them, suddenly you've sized your systems wrong, and the data management system was literally falling over. Jobs would run for 2 days and then die for running out of memory. There are too many stars in the sky. During exercises, we would complain when we would load a scenario for the guider and it wouldn't work correctly, and someone would look and they loaded the wrong file. We say they loaded the wrong sky. After a while, we started to ask, did somebody load the wrong sky? So that's one kind of spectroscopy. The other kind of spectroscopy we do, also multi-object spectroscopy, but using slits. 250,000 tiny little shutters. All right, so the whole array is this big, and there's 250,000 shutters. They're tiny little things, and you open them with static electricity. The bad news is, every once in a while, one of them shorts. That's another story. We're losing shutters. We were supposed to be able to do, there's an allocation for all this stuff. And we've lost I think 12% of the shutters. Some of it to acoustics. Every time you shake the thing, you lose some shutters. So we lost shutters when we did our original vibe test. We lost shutters when we transported it after the cryovac test. And we lost shutters on the way to orbit. Since then, we haven't lost any more shutters to acoustic sources because it's nice and quiet out there. In space, no one can hear you shake. But we have lost shutters to shorts. And we think it's just that as you put out a charge on the shutter and flip it back and forth, every once in a while something gets a little bit too charged and you lose control of the shutter. And we try to lose control closed because if they're open, you can't use that entire row or adjacent rows. This one, there's 235 open shutters, plus the flanking shutter is also open so that you get background reference. And you can do high resolution or what they call low resolution, but low resolution for near spec is still pretty high resolution. And this is of the interstellar medium. So what you're seeing here is what the background looks like. And I forget which is which. Yeah, I don't even know what these are, but yeah, not flux calibrated. So you do see emissions in the interstellar medium. So I promised you a picture of the telescope, and here it is. So on the bottom, the spacecraft bus at the bottom provides communications, power from a solar array, and attitude control, and a rough idea of where we're pointing from the star trackers. The biggest feature of all is this very reflective sunshade. It's 5 layers, thin mylar. It was the thing that scared the hell out of everybody. There are 205 single points of failure on the sun shield alone. They all had to work perfectly on the first try, or we all got to go home. And they all did. We made them as stupid, dumb as possible. Each of the mechanisms had 2 paths for firing, and we fired both paths at once so that we wouldn't get hung up anywhere, and it all worked great. The people at Northrop Grumman did a great job with Sunshine. There were times when we wondered, but they got it right. The telescope itself, this is the baffle that goes into the back where ISOM is. And the telescope is on a backplane. It's on a carbon fiber backplane that's got these 18 segments in 2 rings, A, B, and C segments, mounted to the backplane, and they reflect up to the secondary mirror. Another one of the single points of failure, there's 3 single points of failure on that hinge. If they don't fire, we all go home. They all fired, everything was fine. In fact, this thing over-rotated just slightly, and as a result, the secondary is slightly closer to the primary than we planned. By slightly closer, I mean about 7 microns. Which, when you're trying to get, 80 nanometer precision, that's not insignificant. One of the things you don't see on this telescope is you don't see a big tube. If you've ever seen pictures of Hubble, it's a big tube with wings on it that flap. They do flap. It's annoying how they flap, but that's another mission. In fact, flapping and breathing are the 2 biggest problems with Hubble to this day. Webb has a different problem. It's out there in the open, and as a result, it gets hit by things. Fortunately, they're all very tiny things. If I hold my fingers apart that big, that's still too big. We're talking about things that are just completely infinitesimal, smaller than grains of sand. The typical feature is 20 to 30 microns across. And we just got peppered with them. The ones that are thin circles are ones that don't seem to affect the optical quality except to blow a little bit of the gold plating on the top off. So this is a gold-plated mirror. It's a beryllium with a very thin layer of gold. The total gold on that mirror is about the size of a golf ball. And it was put on with vapor deposition. So they melted the gold and they waited and it all settled down. And then they put a layer of amorphous glass over the top of it. So all of these impacts changed the shape of the mirror just a little bit.
Just the architecture of this thing is mind-blowing. It's amazing.
Most of the impacts are not that big a deal. One of them is, and it's the C3 impact up here. These are pretty typical. They have this little bow tie shape as a result of how they hit. But the C3 one looks different from all the others and is a lot bigger. We think the impact energy here is in the millijoules for most of the impacts. We think the impact for C3 was 7 joules. So it was bad. And as a result, you can really see it. It's the one thing that has messed up our image quality. This is actually my software. We take weak lens images, so we take a +8 and -8 image. What that means is we defocus by 8 waves. So that we get a sort of an image of how the array looks right, how the segment array looks right now. And then we use that to generate these phase maps, and that's the effect that you see on that one segment from the micrometeorite impact. This is a figure error. This is a mistake that was made when they were polishing the mirror. It had this one's hit map loaded, and so they polished it wrong, and we fixed it by hiding it behind the secondary mirror strip. So that one isn't too bad, but this is pretty bad. That's the only one that's a significant uncorrectable error. All the others, most of the effect is you just lose a little throughput. And we started off with so much throughput, we can afford to lose some. And so this is the final alignment image. After we had set the secondary where we wanted it, we intended to leave it there for the rest of the mission, and now we're talking about moving it again. MIRI is up here, the mid-infrared instrument. It sees further into the infrared than anything else. All these guys down here are basically 1 to 5 microns. MIRI goes from 5 to 25. At the very far end, the problem with MIRI is it can actually see the self-heating of the segments from the telescope. And so that just shows up as noise. And so MIRI images are a little bit noisier than all the others. But even so, it's spectacularly good. We had a program to look for water ice on all of the surfaces inside, all the optical surfaces inside the telescope, and we basically didn't find any. Now, remember, we left this thing out in the steamy jungle for 3 days just before we launched it. We kept it in a clean room that was kept at 38% humidity for most of a decade. And yet, wherever the ice went, it didn't land on the optics. The mirrors were much cleaner than we expected. Even at the launch site, the ball guys were going around and very carefully, they used these really fine little paintbrushes, and they were very carefully going through and looking for every little speck of dust and getting it off. And so as a result, there's very little in terms of light scattering, and there's very little in terms of water ice absorption. And as a result, we have a much higher throughput telescope than expected, to the point that we're having to redo our exposure time calculators to make all the exposures shorter. So then we got into science. This is one of the first science observations done. So again, this is NIRCam, this is MIRI. So NIRCam, 1 to 5 microns, it's an infrared image. And you can see that a star in the middle is blowing out all this material. It's not this star, it's this one. It's the smaller, fainter background one, which is, you almost can't see here. It's hidden behind the foreground star. But it's that one there, that's blowing out that thing. This is a pretty well studied object. And for the most part, this was pretty much what we expected, but except for one thing. Look, galaxies. That one's not, that's a star, it's got diffraction spikes. That's a galaxy. Every Webb field is a deep field. This one's so bright it's hard to see galaxies in the background. But this is another nebula it's a star-forming region. This is a good example of the hidden universe. So infrared sees through dust for the most part, especially in the shorter wavelengths. Shorter IR, you see pretty well through dust. There's some weird things going on. Where'd Kevin go? There he is, all the way in the back. Imagine that Kevin's head is a very massive object. He's a pilot, he's got a big head. Light from behind him, light from that fuel truck that went by, will get bent by the mass of his head. If his head was the size of if his head was a couple million megatons, the light would actually bend around and you'd get a ring like that. So there's a foreground galaxy. The blue thing is actually a galaxy. And behind that is another galaxy. It's directly behind it. And so what you're seeing is a ring around that galaxy. That is the background galaxy earlier in the universe. This is the SMAX field. This is this was for a few weeks the deepest image of space ever seen by humans. That's going to be a theme for a few years now. George Ricci and Marcia Ricci have a program to re-image the Hubble Deep Field with NIRCam. And that will be the deepest field ever seen by humans. And then there's another program after that that's going to look at the cosmos field, and there are a whole bunch of deep field things, because we're starting to see that we can see very close to when stars first turn on. This has a couple of interesting features. So this galaxy here, this distorted mess, and this galaxy here are the same galaxy. And let's see, I think it's this galaxy here and this galaxy here and this galaxy. Those are all images of the same galaxy warped around the mass in front of it. How do we know they're the same galaxy, you ask? With spectroscopy. So you look at those two and you use, this is nearest, this is multi-object spectroscopy, slitless multi-object spectroscopy. I'm having trouble saying that today. Of the two galaxies. Now, you notice that this one's a little contaminated, but that one's pretty good. That one's pretty well isolated. This one's just a little bit contaminated. But you see the same hydrogen-oxygen lines at the same distance. And similar, they're similar lines. Wave your hands enough, everything looks similar. So we know those are the same galaxy imaged multiple times. And magnified as well. When you lens a galaxy, when you do gravitational lensing of a galaxy, you also get magnification, just like a regular lens. And so you start to be able to see things that are very, very, very old. So each of these lens galaxies, you do spectroscopy on it with NIRSpec, using those microshutters that I showed you earlier. And you can see here's the hydrogen, oxygen, there's another hydrogen line. This one's further back, this one's further back still. That's the oldest one of all. The universe is only about 13.8 plus or minus 400 million years old. 13.8 billion plus or minus 400 million years old.
So what's the lens in the center, a black hole?
No, it's actually a big galaxy cluster.
Oh.
There's enough mass in the cluster. You can actually do micro lensing with stars if you get lucky enough. But this is a big lens because it's a big galaxy cluster that's got a lot of mass, like Kevin's head. So we're seeing galaxies here that are turning on very early in the history of the universe. One of the questions for a long time was, what comes first, stars or galaxies? How long did it take for the first stars to organize into galaxies? Turns out that's the wrong question. The galaxies were already there. You have to wait for the stars to turn on. Whatever the process was, the galaxies were there first. But you do see some very old stars. That's a star. That's a 12 billion year old star magnified by that lensing event. It's a single star verified by spectroscopy. So that's the oldest star we've seen in the universe as a single star. There's a lot of interesting science going on right now, some of it just by accident. So this is a Cycle 1 program. Every year for Hubble, we would put out a call for proposals, say, tell us your best ideas. We'll pick the 700 best out of the almost 7,000 applications we got. We'll do some observing with it. We've been doing that for many cycles now. 29? Are we on cycle 29 or cycle 30? We've been doing it for a while. Cycle 1, the cycle 2 call for proposal, which will start next July. Cycle 2 will start next July, was just released. And there are some changes from cycle 1. There are new restrictions around micrometeorites. We won't point directly at the direction we're going anymore, starting in cycle 2. And there may be a new science mode. But these guys for cycle 1 said, if we have a good telescope and we have a good model of how that telescope shapes the light, we can find quasars. So quasars are basically, it's a supermassive black hole that's eating a galaxy. And as it eats the material in the galaxy, usually in the galactic core, it emits a whole lot of light as the matter getting pulled into the black hole gets torn apart. It's very energetic. They were first found through X-ray spectroscopy. You can see the shift on the X-rays was just ridiculously high. And so the idea was that if you had really good models, you could figure out what's the supermassive black hole eating things and what are the rest of the stars. And what you'd like to do, because quasars are common in the early universe, is subtract out the light from the supermassive black hole eating things and only look at the stars. Because by looking at the stars, you learn about how star formation happened in the early universe. Well, they were successful. We have a very good telescope. It's very well described. It looks exactly like the model. That very first picture I showed you after the intro shows you how close we are to the model. So we have excellent models, and they can do the point source removal, and they can identify what part is coming from the black hole, from the supermassive black hole eating things, and what part is coming from starlight. But there's an interesting side effect here, especially if you look at this top one here. The supermassive black hole isn't in the middle. It's off center, which means this galaxy is still forming even while it's being eaten. So this black hole has yet to settle down in the middle. If you look at our galaxy, there's a supermassive black hole in the middle. Every once in a while it eats a star. But for the most part, you just see stars orbiting it very fast. You can actually see inertial frame dragging, so we know that supermassive black hole is rotating. Not very fast, fortunately. So they see an off-center supermassive black hole in these primordial galaxies, which is a complete surprise. So much so they haven't really fully, they mention it as an aside and something they'd like to work on in a future cycle. Well, they just got a big win in cycle 1. My guess is they're on the good list for cycle 2. So from very far away to pretty close, this is Neptune. Its ring system really pops out. And you can see 2 of its moons really well, and you can see several more moons as point sources. But don't forget, galaxies. Every Webb field is a deep field. And we can look at individual moons. This is Titan. This is really recent too, and this is weather on Titan. You can see clouds moving around in the upper atmosphere. So the one on the right is Keck 2 days after the James Webb imaging of it. And so you can see that the clouds have moved. It may be that cloud B there is actually dissipating. So they have weather just like we do. Some days they have good flying days and some days they have bad flying days. One of the cool things about Webb though is if you use MIRI, you can look through the top of the atmosphere and see what's underneath it. So the thing on the left is the lower atmosphere, ignoring the clouds on top, because it's an infrared observatory and we can see deeper. You may have heard about the double asteroid redirection test. NASA has for many years been working on a planetary defense system. Rocks get flung in from the outer solar system, and sometimes they come fairly close to Earth, within 500,000 miles. 96 million years ago, one got a lot closer, left a big crater in the Gulf of Mexico, before it was the Gulf of Mexico, and wiped out 80% of the life on the planet. We would like to avoid that if it happens again. One way to do that would be if we spot something coming in, we could just go whack it. Well, we're now 1 for 0. This asteroid was not going to hit us, but we've demonstrated that we can smack an object and change its orbit, and both Hubble and Webb were part of the program to see that ejecta and see how the orbit changed. You can also look at planets that are very far away. I forgot to write down what planet this was. But this uses a technique called phase masking, which is there's a quadrature here. There's 4 masks, and you get different masking of the light in the quadrature. And there's 2 planets here, one here, one here. What persists through all of the phases is a planet. What gets subtracted is not. So we can spot exoplanets. Now this is pretty far out. The little bar on the lower left is 10 times the distance from the sun to the Earth. So these are far out, but we can find them. So Webb will be doing a lot of exoplanet science. Or I guess I should say a lot more exoplanet science. The picture is the digitized sky survey. So that's a ground-based, I think from 2 masks. The star is where the little cartoon star is. There's a little hole in a pickoff mirror that we use as a coronagraph. And so again, to use Kevin's head, if you put a coronagraph right over Kevin's head, you can see what's next to him. And sometimes that's the object you're really interested in. Now, in this case, we're interested in the planet. We know the star's there. We want to see if there's planets there. And sure enough, we can put coronagraphs precisely enough that we can see planets around other stars. All right, this is October's set. the picture on the left is the Hubble picture taken, I don't know, a decade ago. This is Roger Doxey, who was for a long time the Hubble mission head. This is his favorite picture. And people see things in here that can be pretty amusing. Many people said that's the face of the devil. I said that's the face of Blitz, my cat. I miss Blitz. So the picture on the right literally sees through the dust, unveiling what's behind it. Part of the hidden universe. These four stars over here, you can't see them at all in this image, but they sure do pop out in the Webb image. And you can start to see there's star birth in this region and this region. That area, there's a star in the middle that's blowing out all that material, lighting it up from the inside. You can see hints of it in the Hubble image, but you can see it pretty obviously in the Webb image, and especially when you make special pictures for Halloween. So this is the Miri image, and so some of the dust is back. So this is far infrared dust that's been warmed up for a long time, and so now it's emitting light at very long wavelengths as it cools down. And when you put it all together, you get something really cool like this. So I really like that, the way it's lit up from the inside. Okay. This was last week's image. In the center there is so this is another nebula that's getting blown out in the middle. And in the center is a dust lane. And that dust lane is in the process of coalescing into a planetary system. In another billion years, there'll be planets around this star. I don't know who'll be around to see them, but that's what's next for them. So the next time you're out at the full moon, look at where the full moon is at midnight. Midnight Eastern Standard Time, not daylight time. And remember where that is, and go out and look a couple days later, and you'll be looking at Webb. Webb is 1 million miles away, out in the cold and the dark beyond the moon. But you can see it from the bottom. You can see it from the ground. Watch it move. Did you see it? It's a Danish astronomer who likes to check up on us every once in a while. So that's my story.
What a story.
I hope you think you got your $10 billion worth.
Well, thank you, Tom, again.